You can see it tonight. Step outside, look up, and in the right sky, the nearest star beyond our sun is visible to the naked eye. It looks close. It is not. The distance between that star and this planet is so vast that the fastest object humanity has ever built, traveling for nearly 50 years straight, has not crossed even 1% of the gap. But distance is not the real danger. The real danger is what distance does to time. It stretches every emergency into something no one can answer. It turns every small failure into something no one can fix. Between the stars, there is no rescue, no resupply, no second chance. The space between stars does not kill quickly. It kills by making everything take too long. If you find this kind of deep science fascinating, hit like and subscribe. We appreciate everyone who supports this channel. Also, we're now live on Spotify. The link's in the description if you'd like to listen to us wherever you are. Now, are you comfortable? Let's begin. On a clear night, far from city lights, you can look up and see roughly 5,000 stars with the naked eye. They hang there, scattered across the dark, quiet and still. Some of them are faint. Some are bright enough to catch your attention before you even start looking. And there is something about the way they appear that creates a feeling most people never stop to question. They look reachable. Not in a literal sense. Nobody stands in a backyard and thinks they can jump to a star. But the human brain processes distance through experience. And experience says that things you can see clearly are not impossibly far away. A mountain across a valley, a city glowing on the horizon, a ship on the ocean. Your eyes register the object, your mind estimates the gap, and the result is an intuition, a sense that the distance between you and the thing you are looking at is something that could, in principle, be crossed. The stars exploit that intuition. They look like they are part of the same neighborhood as the moon and the planets. A little farther, sure, a little harder to get to, but fundamentally the same kind of distance, just more of it. That feeling is one of the most dangerous misconceptions in all of science, because the distance between stars is not just more of the same distance that separates planets. It is a completely different kind of problem. A kind of problem that does not just make travel harder. It makes survival, communication, rescue, and every system humans depend on slowly fall apart across a gap so wide that most numbers used to describe it lose all meaning before they reach the other side. To understand why, start with the closest star to our sun. It is called Proxima Centauri. It is a small, dim red dwarf, part of the Alpha Centauri system, which contains 3 stars bound together by gravity. Proxima Centauri is the nearest of the 3 to Earth, sitting at a distance of approximately 4.25 light years. That number gets repeated so often in astronomy that it starts to feel routine. 4.25 light years, the nearest star, almost next door by galactic standards. Here is what that number actually means. A light year is the distance that light travels in 1 year. Light moves at roughly 186,000 miles per second. Not per hour, per second. In the time it took you to hear that sentence, a beam of light traveled far enough to circle the Earth more than 7 times. Over the course of a full year, moving at that speed without pause, light covers approximately 5.88 trillion miles. And Proxima Centauri is 4.25 times that distance away. That puts it at roughly 25 trillion miles from Earth. 25 trillion. Written out, that number has 13 digits. It is a distance so large that no direct human experience offers a useful comparison. But we can try. If you could drive a car at highway speed, 70 miles per hour, without ever stopping, without ever sleeping, without ever slowing down for fuel or food or weather, it would take you more than 40 million years to reach Proxima Centauri. 40 million years at highway speed. The entire recorded history of human civilization fits inside the last 10,000 years. You would need to repeat the entire history 4,000 times over, back to back. That is the nearest star. The closest one there is. There is a way to make this distance feel real. Shrink the sun down to the size of a basketball, roughly 9.5 inches across, a ball you could hold in both hands. The Earth, at the same scale, becomes a tiny grain of sand, less than 2 millimeters wide, orbiting the basketball at a distance of roughly 26 meters, about 85 feet. You could stand at the Earth grain and still see the basketball sun, across a parking lot. The solar system feels compact, intimate even. Jupiter is a marble orbiting roughly 135 meters out. Neptune is a smaller bead at about 800 meters. The entire planetary system, everything humans have ever sent a spacecraft to, fits within a circle roughly a mile across. Now find Proxima Centauri on this map. At basketball sun scale, the nearest star is not across the parking lot. It is not across the city. It is not across the state. It is roughly 6,700 kilometers away. That is approximately the distance from New York City to London. On a model where the entire solar system fits within a comfortable walk, the nearest star is an ocean away, and there is nothing between them. No rest stops, no landmarks, no intermediate destinations. Just 6,700 kilometers of empty table, empty floor, empty air, with a basketball at one end and a slightly smaller ball at the other, and absolutely nothing in between. This is the scale of the problem. Not a bigger version of the distances between planets, a categorically different kind of distance. Within the solar system, destinations are scattered across a room. Between the stars, the next room is on another continent. Every mission ever flown, every probe ever launched, every astronaut who has ever floated in the void has operated within that first room. The space between rooms is something else entirely. It is the space where all the rules change, where communication becomes a monologue, where rescue becomes a word without meaning, where the journey stops being defined by distance and starts being defined by how long a machine or a body can last without help. Now consider the fastest object humanity has ever built. The Parker Solar Probe, launched by NASA in 2018, reached a peak speed of approximately 430,000 miles per hour during its close passes around the Sun. At that speed, it could cross the entire United States in about 20 seconds. It is the fastest machine in human history, and even at that velocity, reaching Proxima Centauri would take roughly 6,300 years. The speed record belongs to a machine that was never designed for interstellar travel. It achieved its velocity by falling toward the Sun, and using the star's gravity to accelerate. No existing propulsion system can sustain that speed for an outbound journey, let alone across 4.25 light years of open space. But even if it could, 6,000 years is not a mission. It is a geologic era. Civilizations rise and fall in less time than that. Languages are born and die. Continents shift. 6,000 years ago, humans were just beginning to invent writing. Now consider the Voyager probes, the only human-made objects currently operating in interstellar space. Voyager 1 was launched in 1977. It has been traveling outward from Earth for nearly 49 years. As of 2026, it is approximately 170 astronomical units from Earth, roughly 25 billion kilometers. In November of 2026, it will reach a distance of 1 light day from Earth, meaning a signal traveling at the speed of light will take a full 24 hours just to reach it. 1 light day? That sounds far. It is far, by every human standard. But compared to the distance to Proxima Centauri, it is almost nothing. 1 light day is roughly 1/1500th of a light year. Proxima Centauri is 4¼ light years away. Voyager 1, after nearly half a century of continuous travel, has covered less than 1/10 of 1% of the distance to the nearest star. If Voyager 1 were aimed directly at Proxima Centauri, which it is not, and if it maintained its current speed of roughly 17 kilometers per second, it would arrive in approximately 73,000 years. That is not a typo. 73,000 years. More than 7 times longer than the entirety of recorded human civilization. The pyramids of Egypt were built roughly 4,500 years ago. Multiply that span by 16, and Voyager still would not have arrived. This is the first thing the distance between stars does that the distance between planets does not. It breaks the relationship between speed and arrival. Within our solar system, travel times are measured in months or years. Mars is reachable in roughly 7 months with current technology. Jupiter in about 5 years. Even Pluto, at the far edge of the Sun's planetary family, was reached by New Horizons in 9.5 years. These are long missions. They are not impossible missions. A person who launches a probe to Jupiter can reasonably expect to be alive when the data comes back. Interstellar distances destroy that expectation entirely. They push travel times beyond the span of a single human life, beyond the span of a generation, beyond the span of most governments and institutions. The journey does not merely take a long time. It takes so long that every assumption built into the concept of a mission, that the people who launched it will monitor it, that the technology that built it will still exist when it arrives, that the purpose of the mission will still be relevant, begins to dissolve. And the distance has barely started doing its damage, because travel time is only the first consequence. The second one is worse, and it begins the moment the spacecraft moves far enough from Earth that communication stops being a conversation and becomes something closer to a message in a bottle. Right now, in 2026, it takes roughly 23 hours to send a signal to Voyager 1, and another 23 hours to receive the reply. That is a round-trip communication time of nearly 2 full days. Engineers at the Jet Propulsion Laboratory who managed the Voyager mission have described working under these conditions as a kind of slow correspondence. You send a command on Monday morning, you get a response on Wednesday morning. If something goes wrong, if a thruster misfires, if a memory chip fails, if the spacecraft enters an unexpected orientation, the team on Earth does not learn about it until almost a full day later, and the fix they send does not arrive for another day after that. In 2023, Voyager 1 began sending garbled, unreadable data back to Earth instead of valid telemetry. The cause turned out to be a single failed memory chip in the spacecraft's onboard computer. Engineers had to diagnose the problem using data that took a day to arrive, devise a workaround, write new code, transmit it across billions of miles, wait for the spacecraft to execute it, and then wait again for the results. The entire repair process took months. and Voyager 1 is only 1 light day away, not even close to interstellar distance, just barely past the front porch of the solar system. Now move the clock forward and the spacecraft outward. Imagine a craft en route to Proxima Centauri, 1 year into a multi-decade journey. It is roughly 1 light year from Earth. A signal sent from mission control takes 12 months to arrive. The reply takes another 12 months to come back. The round-trip delay is 2 years. If an anomaly occurs on board, the crew or the autonomous systems must handle it alone for at least 2 years before any guidance from Earth can reach them. And that is only at the 1-year mark, as at the halfway point the delay is over 4 years round trip. By the time the spacecraft is approaching its destination, the communication lag is more than 8 years. This does not simply make communication inconvenient, it makes real-time support impossible. And once real-time support vanishes, something else vanishes with it. Something that every crewed mission in the history of spaceflight has depended on, often without even naming it: rescue. Every human being who has ever traveled to space has done so within reach of rescue. The International Space Station orbits roughly 250 miles above the surface. If a critical system fails, if a fire breaks out, if a medical emergency strikes, the crew can seal themselves into a docked spacecraft and return to Earth within hours. During the Apollo missions, the crew was never more than a few days from home. Even the deepest ambitions of current Mars mission planning assume that the crew will carry enough supplies to wait for a return window and fly back. The round-trip time to Mars is measured in years, but rescue, at least in theory, is part of the architecture. Interstellar distance removes rescue from the architecture entirely. Not as an inconvenience, as a physical impossibility. If a crewed spacecraft is 1 light year from Earth, and a crew member suffers a medical emergency that the onboard systems cannot treat, there is no ship on Earth or anywhere else that can reach them in time to help. The emergency will resolve itself, one way or another, long before any rescue vehicle could be designed, built, launched, and accelerated to interstellar cruise speed. At 2 light years from Earth, the situation is the same. At 3 light years, the same. At 4, the same. The distance is simply too large and the travel times too long for any intervention to arrive within any useful time frame. This means that every failure on an interstellar mission is final. Think about what that changes. In every human spaceflight mission ever flown, the worst-case scenario has always included the possibility of help. An oxygen tank explodes on Apollo 13, and the crew limps home using the lunar module as a lifeboat, guided by engineers on the ground in real time. A cooling loop fails on the International Space Station, and a replacement pump is delivered on the next resupply flight. A cosmonaut develops a dental abscess on Mir, and ground controllers walk the crew through an emergency procedure step by step, in real time. None of that works between the stars. Not the real-time guidance, not the resupply, not the rescue, not the walkthrough, not the second opinion. The spacecraft is alone in a way that no human crew has ever been alone, surrounded by a distance so vast that Earth itself becomes nothing more than a faint signal, arriving months or years too late to matter. And this is not only about crewed missions. Robotic probes face the same isolation in a different form. A robotic spacecraft cannot suffer a heart attack or a psychological breakdown, but it can suffer a software fault, a sensor failure, a navigation error, or a mechanical jam. Within the solar system, these problems are routinely handled through ground intervention. Engineers send diagnostic commands, upload software patches, and instruct the spacecraft to switch to backup systems. The Voyager repair in 2023 is a perfect example. It worked because the delay, while long, was still short enough for a team of human engineers to iterate through diagnosis and repair. At interstellar distances, that iterative process breaks down. A robotic probe 2 light-years from Earth that encounters a navigation error cannot wait 4 years for a corrective command. If its star tracker fails, it must fix itself or drift off course. If its communication antenna shifts out of alignment by a fraction of a degree, the signal back to Earth drops below the detection threshold, and the probe goes silent. Not destroyed, not out of fuel, just pointed in the wrong direction, unable to phone home, drifting through the dark with all its instruments intact, and no one listening. The engineers who manage the Voyager missions have described the current situation in terms that carry a quiet warning for any future interstellar effort. As of 2026, Voyager 1 has only 2 operational science instruments remaining: the magnetometer and the plasma wave subsystem. Its radioisotope power supply loses roughly 4 watts of output per year. Its hydrazine thruster lines are partially clogged. It has no backup for its thruster system. Everything on board is what engineers call single string, meaning there is no redundancy left. If one more critical component fails, the spacecraft may not be recoverable. And Voyager 1 is less than 1 light day from Earth. It can still talk to us. We can still talk to it. If a thruster fails tomorrow, the team at the Jet Propulsion Laboratory will know within 24 hours. They will have options. They will be able to try things. A spacecraft at interstellar distance has none of that. No team standing by, no diagnostic loop, no backup plan that involves anyone other than whatever is on board. The only resources available are the ones the spacecraft brought with it. The only repairs possible are the ones the spacecraft can perform on itself. The only decisions that matter are the ones made autonomously, in the dark, light years from the nearest human mind. This is the transformation that interstellar distance forces on every mission concept. It does not merely make the journey longer. It changes the fundamental nature of what a mission is. Within the solar system, a mission is a collaboration between a spacecraft and a ground team. A shared effort where problems are solved through communication, iteration, and the ability to send help when things go wrong. Between the stars, that collaboration dissolves. The ground team becomes a distant memory. Communication becomes a monologue arriving years late. And the spacecraft, whether robotic or crewed, becomes the entire mission, carrying every answer it will ever have, crossing a distance that does not care whether it arrives intact or as a hollow shell. The gap between Earth and Proxima Centauri is not a road. It is an isolation chamber measured in light years, and the longer a spacecraft spends inside it, the more the supports that every mission in history has relied on are stripped away, one by one, until nothing is left but the machine and the void. The question that should follow is straightforward. If the spacecraft brings everything it needs, if it carries enough fuel, enough food, enough spare parts, enough intelligence to operate on its own, then what exactly is the problem? What makes the distance between stars more dangerous than just a very long version of the distance between planets? The answer is time. Not time as a clock on a wall. Time as a weapon. Because the gap between stars does not just separate places. It stretches the exposure to every hazard that exists in deep space across years, across decades, across centuries. Hazards that are manageable over a 7-month trip to Mars become something entirely different when they are sustained for 40 years, or 400, or 4,000. Radiation that a Mars crew can tolerate for a round trip becomes a cumulative death sentence over decades of interstellar exposure. Dust particles that a planetary probe can shrug off become surface-eroding projectiles when the spacecraft passes through trillions of miles of interstellar medium. Power systems that function reliably for a 15-year planetary mission decay below usable output on interstellar timescales. Electronic components that withstand a decade of operation begin to drift, degrade, and fail when asked to work for a century. Every one of these hazards exists within the solar system. Every one of them is manageable over the distances and timescales that current missions demand. The difference is not the hazard itself. The difference is how long the spacecraft must endure it. And interstellar distance, because it forces interstellar travel times, stretches that endurance requirement past the breaking point of every material, every machine, and every biological system that has ever been tested. Distance creates duration, duration creates exposure, exposure creates cumulative failure, and cumulative failure between the stars becomes final failure, because no rescue can arrive. That chain of consequences is the real danger of the distance between stars. Not a single dramatic threat, not an explosion, not a monster. A slow, grinding accumulation of damage that builds across the emptiness, year after year, until the spacecraft that left Earth as a functioning mission arrives at its destination as something else entirely, or does not arrive at all. What the accumulation looks like, hazard by hazard, system by system, is what makes the space between stars more hostile than almost anyone imagines. And it begins with something invisible, silent, and impossible to fully stop. Something that fills every cubic centimeter of the void between here and the nearest star, and has been doing damage to everything it touches since the universe began. The space between stars is not empty. It looks empty. Every image ever taken of the void between stellar systems shows blackness. Nothing. A gap so clean it seems sterile. But that blackness is filled with things you cannot see. Things that have been moving through it since long before the Earth existed. And every one of them is waiting to do damage. The first thing an interstellar spacecraft loses is something most mission plans never mention. Because within the solar system, it has always been there. The heliosphere. The sun does not simply emit light and heat. It emits a continuous wind of charged particles, protons and electrons and helium nuclei, like streaming outward in every direction at speeds of roughly 400 kilometers per second. This solar wind inflates a vast bubble around the sun that extends far past the orbit of Pluto, roughly 120 astronomical units in every direction. That bubble is the heliosphere, and everything humanity has ever built, every satellite, every space station, every planetary probe, has operated inside it. The heliosphere is not an impenetrable wall, but it is a shield. The outward pressure of the solar wind pushes against the incoming flux of galactic cosmic rays, deflecting a significant portion of them before they reach the inner solar system. The effect is measurable and substantial. Inside the heliosphere, the galactic cosmic ray intensity is roughly 30 to 50% lower than it is in the interstellar medium beyond. The sun's magnetic field, carried outward by the solar wind, adds another layer of deflection bending the paths of incoming charged particles and reducing the flux further. This is why astronauts on the International Space Station, orbiting within Earth's own magnetosphere inside the heliosphere, receive a radiation dose that is concerning but survivable. They are protected by two nested magnetic shields, the planets and the stars, layered on top of each other. An interstellar spacecraft loses both of those shields. The first to go is Earth's magnetosphere, left behind within minutes of departure. The second, the heliosphere, is left behind after the spacecraft crosses the heliopause, the boundary where the solar wind can no longer push back against the pressure of the interstellar medium. Voyager 1 crossed this boundary in August of 2012 at a distance of roughly 121 astronomical units from the Sun. Voyager 2 crossed it in November of 2018 at a similar distance. Both spacecraft recorded the crossing in their instruments. The solar wind dropped to near zero. The density of galactic cosmic rays jumped sharply. The magnetic field changed character, shifting from the Sun's outward flowing field to the ambient magnetic field of the interstellar medium. For the Voyager probes, this transition was a scientific milestone. For a future interstellar mission, it would be something else entirely. It would be the moment the mission loses its last natural protection against the full intensity of galactic cosmic ray radiation. From that point forward, every particle that the heliosphere had been deflecting now strikes the spacecraft directly. The radiation environment does not increase gradually as the spacecraft moves outward. It increases in a step, a measurable jump at the heliopause, and then remains at that elevated level for the entire remainder of the journey. This matters because every radiation dose estimate for an interstellar mission must be calculated using the flux levels outside the heliosphere, not inside it. Studies conducted using data from within the solar system, including most of the radiation research done for Mars mission planning, underestimate the interstellar exposure by a significant margin. The spacecraft is not merely traveling farther from the Sun, it is leaving the Sun's protection entirely, stepping out from behind a shield that has been deflecting a third or more of the incoming galactic radiation, and exposing itself to the full, unfiltered particle flux of the Milky Way. And that exposure begins not at some remote point in the journey, but relatively early. The heliopause is roughly 120 astronomical units from the Sun. At 10% of the speed of light, a spacecraft would cross it in less than a week after departure. Within days of leaving Earth, the mission would already be operating in the full interstellar radiation environment, with the entire multi-decade journey still ahead. The shield is gone almost before the journey begins. The first and most persistent of these invisible threats is radiation. Not the kind that comes from a nuclear accident or an X-ray machine. A different kind, older, faster, harder to stop, and spread across every cubic centimeter of the galaxy with no gaps, no safe zones, and no off switch. They are called galactic cosmic rays. They are not rays in the way most people picture them, not beams of light or waves of energy. They are particles, individual atomic nuclei, mostly hydrogen and helium, but also heavier elements like iron and carbon, stripped of their electrons and accelerated to extraordinary speeds by the most violent events in the universe: supernova explosions, colliding neutron stars, the turbulent magnetic fields of the Milky Way itself. These events act like cosmic accelerators, flinging particles outward at velocities approaching the speed of light, and once launched, those particles travel for millions of years. crossing the galaxy in every direction, filling interstellar space with a constant, invisible rain of high-energy matter. On Earth, you're protected from almost all of it. The planet's magnetic field deflects the majority of incoming particles. The atmosphere absorbs most of what gets through. By the time galactic cosmic rays reach the surface, their intensity has been reduced to a tiny fraction of what exists in open space. You absorb a small dose every day without knowing it, roughly equivalent to a few dental X-rays per year. In interstellar space, there is no magnetic field to hide behind. There is no atmosphere. There is nothing between the spacecraft and the full intensity of the galactic cosmic ray flux, except whatever shielding the spacecraft brought with it. And here is the problem that has troubled radiation physicists for decades. You cannot fully shield against galactic cosmic rays, not with any known material, not with any practical amount of mass. The reason is energy. A typical galactic cosmic ray particle carries kinetic energy measured in billions of electron volts. Some carry trillions. At these energies, the particles do not simply bounce off a metal hull, they punch through it. When a high-energy cosmic ray strikes a layer of shielding, it does not stop cleanly. It collides with the atoms in the shielding material and shatters them, producing a spray of secondary particles, neutrons, protons, pions, fragments of nuclei that scatter inward through the spacecraft in a cascade. In many cases, the secondary radiation produced by the shielding is more biologically damaging than the original particle would have been. Adding more shielding can make the problem worse, not better, depending on the material and the energy of the incoming particle. This is not a theoretical concern. NASA has studied it extensively for Mars mission planning, and the conclusion is consistent across multiple research programs. Passive shielding alone cannot reduce galactic cosmic ray exposure to safe levels for long-duration missions. Active shielding concepts, using powerful magnetic or electrostatic fields to deflect incoming particles, have been proposed, but none have been built or tested at the scale required for an interstellar vehicle. What this means for a spacecraft crossing the distance to even the nearest star is straightforward and grim. Every day of the journey, every week, every month, every year, the crew and the electronics on board absorb a dose of high-energy radiation that cannot be entirely blocked. On a 7-month trip to Mars, the cumulative dose is concerning but manageable. NASA estimates that a round trip to Mars would expose astronauts to roughly 1 full sievert of radiation, enough to measurably increase lifetime cancer risk, but within the bounds of what agencies have been willing to accept. Now extend that exposure across the timescales that interstellar travel demands. A journey to Proxima Centauri at 10% of the speed of light, an extremely ambitious speed that no existing technology can achieve, would take roughly 43 years. 43 years of continuous cosmic ray exposure. At the flux levels measured in interstellar space, which are higher than those inside the heliosphere because the sun's magnetic field provides a partial shield within our solar system, the cumulative dose over 4 decades would be enormous. Multiple sieverts, possibly tens of sieverts, depending on shielding effectiveness and solar cycle conditions during departure. The biological consequences of that exposure are not speculative, they are documented. Sustained high-dose radiation damages DNA. The body repairs most of this damage, but the repair mechanisms are imperfect, and over time the errors accumulate. Cancer risk rises, cardiovascular disease risk rises, neurological damage accumulates, Studies on astronauts who have spent extended periods on the International Space Station, which orbits within Earth's protective magnetosphere, have shown measurable increases in cataract formation, immune system suppression, and changes in brain structure after missions lasting only 6 to 12 months. Interstellar travel demands exposures hundreds of times longer, in an environment with higher flux and higher particle energies, and the biological damage is only half the equation. Galactic cosmic rays also degrade electronics. When a high-energy particle passes through a semiconductor chip, it can deposit enough charge to flip a data bit from 1 to 0 or 0 to 1. This is called a single-event upset, and it happens routinely to satellites in Earth orbit. In most cases, error-correcting software catches and fixes the flip bit before it causes a problem. But over decades of interstellar travel, the cumulative rate of single-event upsets rises into the millions. Some fraction of those upsets will evade correction. Some will corrupt critical navigation data. Some will alter stored commands. Some will cause what engineers call latch-up events, where a particle strike sends a circuit into a permanent high-current state that can burn out the component entirely. Beyond individual particle strikes, there is the cumulative effect of total ionizing dose, the slow degradation of semiconductor materials as radiation exposure builds over time. Transistors become leaky, threshold voltages drift, timing margins shrink. The electronics do not fail in a single dramatic moment. They get slightly worse year after year until the performance margin that separated a functioning system from a failed one quietly disappears. Every piece of electronics on an interstellar spacecraft would need to withstand decades of this punishment. Every processor, every memory chip, every sensor, every communication circuit. And each one would need to do so without the possibility of replacement, because there are no spare parts waiting at the next port, and the nearest fabrication facility is light years behind. Radiation is the first slow destroyer. It works constantly. It cannot be fully stopped. And its damage accumulates with time in a way that turns a manageable hazard into an existential one simply by stretching the journey long enough. The second slow destroyer is already waiting in the path of any interstellar spacecraft, and it is even harder to see. The interstellar medium, the material that fills the space between stars, is extraordinarily thin. If you could scoop up a cubic centimeter of interstellar space, you would find, on average, roughly 1 atom in it. By earthly standards, that is a better vacuum than anything achievable in a laboratory. It sounds like nothing. It sounds harmless. It is neither. The problem is distance. A spacecraft traveling to Proxima Centauri must cross approximately 4.25 light years of this medium. That is roughly 40 trillion kilometers. Even at a density of 1 atom per cubic centimeter, the total amount of material swept up by the spacecraft's frontal cross-section over that distance is not trivial. For a spacecraft with a forward-facing area of a few square meters, the accumulated mass of interstellar gas encountered over the full journey amounts to milligrams or grams of hydrogen and helium, depending on the spacecraft's size and the local density of the medium. At low speeds, this gas is harmless. The atoms drift past or bounce off the hull with negligible energy. But speed changes everything. At 10% of the speed of light, roughly 30,000 kilometers per second, each hydrogen atom that strikes the spacecraft carries kinetic energy equivalent to a fast-moving particle in a physics experiment. The individual impact is small, but the rate is high. Millions of atoms per second per square centimeter of forward surface. The cumulative effect is a slow, steady bombardment that heats the forward surface of the spacecraft, erodes its material layer by layer, and implants hydrogen atoms into the whole structure where they can form bubbles, cause blistering, and weaken the material from within. Interstellar dust makes this worse. Dust grains, tiny solid particles of silicate, carbon, and ice, are far less common than gas atoms, but they are far more massive. A typical interstellar dust grain is smaller than a red blood cell, roughly 1/10 of a micron across, and weighs only a tiny fraction of a milligram. At rest, it is completely harmless. At 10% of the speed of light, it is a microscopic bullet carrying enough kinetic energy to vaporize itself, and a small crater of whole material on impact. Research published by scientists at Lawrence Livermore National Laboratory examined what happens when a dust grain strikes a spacecraft, traveling at 20% of the speed of light. The grain passes into the hole in roughly 20 femtoseconds, a time interval so short that light itself moves only a few microns during the collision. The grain's atoms are instantly ionized by the energy of impact. The material around the impact point is superheated and ejected, forming a tiny explosion that excavates a crater many times larger than the grain itself. Each individual impact is small, but over 4.25 light years of travel, the spacecraft encounters billions of these grains. The forward surface is not hit once. It is sandblasted continuously for the entire duration of the journey, each grain leaving its mark, each crater overlapping with the ones beside it, until the surface is eroded to a measurable depth. Studies have estimated that at 20% of the speed of light, the erosion from interstellar dust alone could remove roughly 0.5 millimeter of hull material over the distance to Alpha Centauri. That may sound small, but for lightweight structures, for sensor windows, for optical surfaces, for thermal radiators, 0.5 millimeter is significant. It changes the reflectivity of surfaces. It degrades the transparency of windows. It alters the thermal properties of the hull, and it does so gradually, invisibly, without any single impact large enough to trigger an alarm. The spacecraft does not know it is being eroded. It simply becomes, over time, slightly less capable of doing everything it was designed to do. At higher speeds, the problem escalates. At 50% of the speed of light, the kinetic energy of each dust grain impact rises by more than an order of magnitude. A grain that produced a small crater at 10% of light speed produces a deep puncture at 50%. And the accumulated energy deposited into the hull becomes large enough to cause structural heating, thermal stress, and potential failure of forward-facing components. There is a third slow destroyer that operates alongside radiation and dust, and it is so fundamental to the physics of space that it is easy to overlook. Temperature, not cold, exactly. The problem is more subtle than that. The problem is that interstellar space offers no way to manage heat except through radiation, and radiation cooling is slow, inefficient, and dependent on surfaces that degrade over time. On Earth, heat management is simple. You blow air over something hot. You run water through it. You put it in contact with something cooler. All of these methods rely on conduction or convection, the transfer of heat through physical contact with another material or fluid. In space, neither works. The interstellar medium contains roughly 1 atom per cubic centimeter. That is not a gas. It is a vacuum so extreme that no meaningful heat can be transferred to it. The only remaining option is radiative cooling. A hot surface emits infrared photons, and each photon carries a tiny amount of energy away. This is how every spacecraft ever built has managed its thermal budget. Radiator panels, usually large flat surfaces coated with materials designed to emit infrared radiation efficiently, face outward into space and glow away the excess heat generated by electronics, life support systems, and absorbed sunlight. Inside the solar system, this process works reasonably well. The distances are short enough and the mission durations brief enough that radiator surfaces maintain their performance. But across interstellar timescales, the radiators themselves become a vulnerability. Their coatings degrade under cosmic ray bombardment. Micrometeorite and dust impacts pit and roughen the surface, changing its emissivity. Over decades, the radiators become less efficient at shedding heat. The spacecraft gets slightly warmer. Electronics that were designed to operate within a specific temperature range begin to operate outside it. Components that were thermally stable become thermally stressed. The margins that kept everything within acceptable limits slowly evaporate. And the problem works in both directions. A spacecraft in interstellar space, far from any star, receives negligible external heat input. The cosmic microwave background radiation, the faint thermal echo of the Big Bang, provides an ambient temperature of roughly 2.7 degrees above absolute zero. Without internal heat sources, the spacecraft would cool to that temperature, far too cold for any electronic component or biological system to function. This means the spacecraft must actively heat itself, using power from its onboard generators to maintain habitable and operable temperatures throughout the vehicle. For a crewed spacecraft, this means heating crew quarters, maintaining water in liquid form, keeping food storage above freezing, and preventing biological waste recycling systems from seizing up. For a robotic probe, it means keeping batteries above their minimum operating temperature, preventing propellant lines from freezing, and maintaining sensors within their calibrated range. Every one of these heating demands consumes power, and as established, power is the resource that declines most reliably and most irreversibly over interstellar timescales. The thermal problem therefore compounds the power problem. As the power source decays, the spacecraft's ability to keep itself warm diminishes. As temperatures drop, components begin to operate outside their design range. As components degrade, their power consumption may change unpredictably, drawing more current in some cases, less in others, further disrupting the thermal balance. The spacecraft enters a slow spiral where thermal management, power generation, and component performance are all coupled, all declining, and all pulling each other downward. Voyager 1 has already experienced a version of this. As its radioisotope generators declined, engineers turned off onboard heaters to conserve power. The spacecraft's internal temperatures dropped. Some components began operating at temperatures below their originally intended range. The team accepted this because the alternative, keeping heaters on and running out of power for science instruments, was worse. It was a managed retreat, trading thermal margin for operational longevity. An interstellar spacecraft would face the same trade, but across a much longer timeline and without a ground team to make the decisions. Radiation, dust, and thermal erosion are three environmental threats that fill interstellar space or emerge from the conditions of traveling through it. They are always present. They are always doing damage. and they are all governed by the same merciless arithmetic. The longer the journey, the greater the total exposure. Distance creates duration, duration creates accumulation, and accumulation, unchecked by any repair or replacement, creates failure. But the spacecraft is not only being attacked from the outside, it is also decaying from within. Every machine ever built begins to age the moment it is assembled. Materials fatigue, lubricants break down, seals degrade, solder joints develop micro cracks, capacitors drift, bearings wear. This is true of a car, a washing machine, a satellite, and a spacecraft. The question is never whether a machine will degrade, but how long it can operate before the degradation compromises its function. For most space missions, the answer is comfortably within the mission timeline. A Mars rover is designed to last at least 2 years on the surface. The Cassini spacecraft operated for 20 years around Saturn. The Hubble Space Telescope has been functioning for over 35 years, sustained by periodic servicing missions that replaced failing components. Each of these machines was designed for a specific operational lifetime, and each has either met or exceeded it. Interstellar travel demands operational lifetimes that dwarf any of these. A journey at 10% of the speed of light takes over 40 years. At 1%, over 400 years. At the speed of Voyager 1, over 70,000 years. There is no engineering precedent for machines that must function reliably across these timescales. None. The closest thing we have to a test case is Voyager itself. And the story it tells is a cautionary one. Voyager 1 was built in the mid-1970s using the best technology available at the time. Its electronics are simple by modern standards, which in some ways has been an advantage. Simpler systems have fewer failure modes, but even with that simplicity, the spacecraft has been losing capability steadily for decades. Its cameras were shut down in 1990, not because they failed, but because there was nothing close enough to photograph and the power was needed elsewhere. Its radioisotope thermoelectric generators, which convert the heat from decaying plutonium-238 into electricity, have been declining in output since launch. At launch, they produced roughly 470 watts. As of 2026, they produce roughly 220 watts, less than half their original capacity. The power loss follows the physics of radioactive decay. Plutonium-238 has a half-life of approximately 88 years, meaning the thermal output of the fuel drops by half every 88 years. But the thermoelectric converters that turn heat into electricity also degrade over time. The combined effect is a steady, irreversible decline in available power that forces engineers to shut down systems one by one to keep the remaining instruments alive. In March of 2025, NASA turned off Voyager 1's cosmic ray subsystem, the instrument that helped confirm the spacecraft's crossing into interstellar space a decade earlier. In April of 2026, the low-energy charged particle instrument was shut down as well. As of mid-2026, only 2 science instruments remain operational: the magnetometer and the plasma wave subsystem. Everything else is off. The spacecraft is still transmitting. It is still being commanded. But it is a shadow of what it was at launch, stripped down to its minimum functional state by the slow, relentless arithmetic of power decay. And Voyager 1 is not even 50 years old. An interstellar mission would need to sustain full operational capability for far longer, decades at minimum, centuries in many proposed scenarios, and the power problem does not scale linearly. It compounds. As power declines, heaters are turned off. Without heaters, temperatures inside the spacecraft drop. Lower temperatures change the behavior of lubricants, batteries, and electronic components. Some materials become brittle. Some circuits operate outside the design temperature range. The spacecraft begins to experience failures not because any individual component has reached its rated lifetime, but because the environment inside the spacecraft has changed in ways the components were never designed to tolerate. This is what engineers call cascading degradation. One system's decline creates stress on another system, which accelerates its decline, which stresses a third system, and so on. Each failure does not just remove one capability, it shifts the load onto the surviving systems, pushing them closer to their own limits. On Voyager 1, this process has been managed through extraordinary engineering discipline. The team at the Jet Propulsion Laboratory has nursed the spacecraft through multiple crises, improvising solutions with hardware designed half a century ago, using a communication link that takes almost a full day in each direction. They have kept the spacecraft alive far beyond its original design lifetime, which is a remarkable achievement. But they have done so by accepting a steady reduction in capability. Voyager 1 today can do far less than Voyager 1 in 1980. It is a machine in managed decline. Between May of 2025 and February of 2026, Deep Space Station 43 in Canberra, Australia, the only antenna on Earth capable of sending commands to both Voyager spacecraft, was taken offline for major upgrades. During that period, the Voyager team had only limited communication windows with their spacecraft. If a critical failure had occurred during the blackout, the team might not have been able to respond in time. The spacecraft would have been on their own, relying entirely on their onboard autonomous fault protection systems, designed in the early 1970s to save themselves. This is a preview of interstellar reality, not the managed, supported, carefully monitored decline of a spacecraft that still has a ground team and a communication link, but the unmanaged, unsupported, completely autonomous decline of a machine that left its ground team behind years or decades ago and must keep itself alive with no external help, no replacement parts, and no second opinions. The issue is not whether an interstellar spacecraft would carry redundant systems. Of course it would. Every critical component would have backups. Some would have backups for the backups. But redundancy is a finite resource, and interstellar distance consumes it the same way it consumes everything else, through time. A spacecraft with triple redundant navigation computers is robust against the failure of one computer. It is survivable after the failure of two. It is dead after the failure of three. If the mean time between failures for each computer is 15 years, then triple redundancy provides statistical protection for roughly 45 years. That might be enough for a fast interstellar mission. It is nowhere near enough for a slow one. And every other redundant system on board follows the same math. 3 backup gyroscopes, 3 backup communication amplifiers, 3 backup reaction wheels. Each one is a candle burning down at its own rate, and the journey is very, very long. This is the machinery of interstellar danger, not a single dramatic hazard, not an asteroid collision or a stellar flare or a hull breach. A slow, quiet erosion of everything the mission depends on, running in parallel across every system simultaneously. Radiation degrades the electronics and the biology. Dust erodes the surfaces and the sensors. Power decays according to physics that cannot be argued with. Mechanical systems age according to material properties that cannot be suspended. And redundancy, the last line of defense, is consumed one backup at a time until nothing is left but the primary system, running on borrowed time, with no replacement anywhere in the universe that could arrive before it fails. The spacecraft is still moving. The distance behind it is growing. The distance ahead is shrinking. But the machine that left Earth as a fully capable mission is becoming, year by year, something less. Something quieter. Something closer to an object than a mission. And there is a temptation, when you see this picture, to reach for the obvious solution. Go faster. Shorten the journey. Reduce the time that radiation, dust, power loss, and aging have to do their work. Compress the trip from centuries to decades, from decades to years. It sounds like the answer. It is not. Because speed in interstellar space does not simply solve the problem of duration. It creates an entirely new category of problems, and some of them are worse than the ones it was supposed to fix. There is an instinct, when confronted with that slow destruction, to reach for an obvious answer. If time is the enemy, reduce the time. If decades of exposure to radiation, dust, and system aging are what kill the mission, then shorten the journey. Accelerate faster. Travel at a higher fraction of the speed of light. Compress the trip from centuries into decades, from decades into years. Outrun the damage. It is the most intuitive solution imaginable, and it is a trap. Because speed, in interstellar space, does not simply reduce one set of problems. It introduces an entirely new set. Some of them are as dangerous as the hazard speed was supposed to eliminate. A few of them are worse. The distance between stars creates a paradox with no clean resolution. Travel slowly, and the journey takes so long that the spacecraft degrades before arrival. Travel quickly, and the journey becomes so violent that the spacecraft may not survive the trip at all. There is no comfortable middle ground. There is only a narrow, punishing window where both sets of dangers are survivable, and finding that window requires understanding exactly what speed does to a vehicle moving between the stars. It begins with a law of physics so basic that most people learn it in school and then forget it. Kinetic energy scales with the square velocity, not linearly, not proportionally, with the square. This means that doubling your speed does not double the energy of a collision, it quadruples it. Tripling your speed does not triple the energy, it multiplies it by 9. At 10 times the speed, the energy is 100 times greater. This law governs everything that happens to a spacecraft moving at high velocity through the interstellar medium. Every atom of hydrogen, every speck of dust, every stray particle that the spacecraft encounters delivers an impact whose energy depends on how fast the spacecraft is moving. At the relatively modest speed of Voyager 1, roughly 17 kilometers per second, those encounters are negligible. The atoms bounce off. The dust grains leave microscopic marks. Nothing important happens. At 1% of the speed of light, roughly 3,000 kilometers per second, the physics changes. Each hydrogen atom now strikes the forward surface with the energy of a low-grade particle accelerator. The individual impact is still small, but the sheer number of atoms encountered per second per square centimeter of hull begins to add up. The spacecraft's forward surface heats, not dramatically, not dangerously at this speed, but measurably. The interstellar medium, which seemed like nothing at Voyager speeds, has become a faint but constant thermal load pressing against the nose of the spacecraft. At 10% of the speed of light, 30,000 kilometers per second, the transformation is severe. Each hydrogen atom now carries enough kinetic energy to behave like a particle in a high-energy physics experiment. The stream of interstellar gas striking the spacecraft's bow is no longer a gentle breeze. It is a focused beam of relativistic nucleons. A bombardment of protons and helium nuclei arriving with energies measured in millions of electron volts. This is not a metaphor. Research published in nuclear physics and astrophysics journals has established clearly that at 10% of light speed and above, the oncoming flow of interstellar gas itself becomes a radiation source, not a secondary effect, not a complication, a primary hazard. The spacecraft is flying face first into a particle beam generated by its own velocity. The radiation dose absorbed by an unshielded astronaut at the front of a spacecraft, moving at 20% of the speed of light through typical interstellar medium, has been calculated. The numbers are not subtle. Hundreds of rems per second, thousands of rems per second at higher velocities. For context, a lethal dose of radiation for a human being is roughly 400 rems delivered over a short period. At 20% of light speed, the forward-facing surfaces of the spacecraft receive a lethal human dose every fraction of a second, delivered not by some exotic weapon, but by the harmless hydrogen gas that fills the space between stars, transformed into a killing field by the spacecraft's own motion. Shielding against this bombardment is possible in principle. A dense forward shield, a block of material thick enough to absorb the incoming proton flux and its secondary cascade, could protect the crew quarters and sensitive electronics behind it. But that shield has mass, and mass is the single most expensive commodity on any spacecraft. This is where the arithmetic turns cruel. Every kilogram added to a spacecraft's mass increases the amount of energy required to accelerate it. For conventional rocket propulsion, the relationship is exponential. The fuel required to accelerate a given payload to a given speed grows exponentially with the mass of the payload. This is the tyranny of the rocket equation, and it applies to every propulsion concept that carries its own fuel. If you add a 10-ton radiation shield to the front of your spacecraft, you do not simply need 10 tons more fuel. You need exponentially more fuel to accelerate the extra mass of the shield, plus exponentially more fuel to accelerate the extra fuel, plus more fuel to accelerate that fuel, and so on. The total launch mass balloons far beyond any practical limit. This creates a vicious cycle. Higher speed means more radiation from the interstellar medium. More radiation requires more shielding. More shielding means more mass. More mass requires more fuel. More fuel means more mass again. Each step in the chain makes the next step worse, until the spacecraft design becomes an impossibility. A vehicle so heavy with shielding and fuel that no propulsion system can accelerate it to the speed it needs to justify the shielding in the first place. Some propulsion concepts attempt to escape this cycle by not carrying fuel at all. The most prominent is the laser sail, the concept behind the breakthrough Starshot initiative. The idea is elegant. Instead of carrying fuel, the spacecraft carries an enormous, ultra-thin reflective sail, a ground-based laser array powered by the energy grid of an entire civilization fires a beam at the sail. The pressure of the laser light pushes the spacecraft forward. No onboard fuel required. No rocket equation. The spacecraft is light. The acceleration is intense, and speeds of 20% of light speed are theoretically achievable. But the laser sail does not escape the speed paradox. It merely shifts the problem to a different part of the mission. First, the acceleration phase is extraordinary in its violence. To reach 20% of light speed, the breakthrough Starshot design called for gram-scale spacecraft, tiny chips weighing a few grams each, to be accelerated by a 100 gigawatt laser array for approximately 10 minutes. The acceleration during those 10 minutes is on the order of tens of thousands of G-forces. No human could survive it. No conventional electronic component could survive it without being specially hardened. The concept is designed exclusively for robotic probes, so small and so simple that they can be treated as nearly disposable. And they would need to be, because the second problem. At 20% of light speed, the interstellar dust environment becomes lethal on a per particle basis. Each grain that strikes the sail or the chip delivers enough energy to vaporize material and excavate a crater. The breakthrough Starshot design accounted for this by planning to launch swarms of roughly 1,000 identical probes, accepting that many would be damaged or destroyed by dust impacts during the 4.25-year transit. Redundancy through sheer numbers. The mission would succeed if even a handful survived to reach the Alpha Centauri system. That is a viable strategy for a gram-scale chip. It is not a viable strategy for a crewed spacecraft, or even for a large robotic probe carrying sophisticated instruments. You cannot launch 1,000 copies of a crewed vessel and hope some of them make it. The dust problem at high speed does not have a brute force solution for any mission that carries meaningful mass. And even if the dust could be survived, even if the radiation could be shielded, even if the thermal load could be managed, there is a problem waiting at the end of the journey that is arguably worse than anything encountered along the way: deceleration. This is the detail that most public discussions of interstellar travel skip over entirely, and it is the detail that most thoroughly destroys the fantasy of fast interstellar flight. A spacecraft that accelerates to 10% of the speed of light for the purpose of reaching another star system does not simply arrive and stop. It arrives at 10% of the speed of light. That is 30,000 kilometers per second. At that velocity, the spacecraft would cross the entire Earth-to-Sun distance in approximately 83 minutes. It would pass through the Alpha Centauri system from one edge of the habitable zone to the other in a matter of hours. It would flash past Proxima b like a bullet past a window pane. No orbit insertion, no landing, no extended observation, just a brief, screaming flyby and then onward into the void, unable to stop, unable to turn around, committed to traveling away from its destination forever. For a flyby mission, this might be acceptable. The breakthrough Starshot concept was designed as a flyby. The tiny probes would snap a few images as they screamed through the system at 20% of light speed and transmit them back to Earth. The data would be limited, the encounter brief, and the probes would continue into deep space, never to be recovered. For a first look at another star system, it might be enough. But for any mission that intends to do more than glance, for any mission that wants to enter orbit, deploy instruments, study a planet's surface, or deliver a crew, deceleration is not optional. The spacecraft must slow down. And slowing down from interstellar cruise speed requires almost exactly as much energy as speeding up to it. This is the part that breaks most mission designs. For a spacecraft carrying its own fuel, the deceleration requirement effectively doubles the propulsion budget. The ship must carry enough fuel to accelerate to cruise speed, and enough fuel to decelerate from cruise speed back to a velocity where orbital insertion or planetary approach is possible. But because of the rocket equation, carrying twice the fuel does not merely double the launch mass. It increases it exponentially. A spacecraft that needs 1,000 tons of fuel to reach 10% of light speed might need 10,000 tons or more to also stop at the destination. The mass penalty for deceleration is so severe that most serious interstellar mission studies have spent more time wrestling with the braking problem than the acceleration problem. Project Daedalus, a detailed interstellar probe study conducted by the British Interplanetary Society in the 1970s, designed a fusion-powered spacecraft that could reach roughly 12% of light speed. The study concluded that deceleration at the destination was not feasible with the proposed design. The probe would perform a flyby only. No orbit. No stop. One pass and gone. Project Daedalus was not a thought experiment. It was a rigorous engineering study involving dozens of specialists over several years. And the conclusion was that even with fusion propulsion, a technology far beyond current capability, stopping at the destination was too expensive in mass and fuel to be practical. Later studies have explored alternative braking methods. One proposal is magnetic sail braking, where a spacecraft deploys an enormous superconducting loop that generates a magnetic field large enough to interact with the interstellar medium, creating drag that gradually slows the spacecraft over years or decades. The physics is sound in principle, but the engineering is staggering. The magnetic sail would need to be kilometers in diameter. The superconducting materials would need to function for years in the harsh interstellar environment. The deceleration would be slow, adding years or decades to the arrival phase, during which the spacecraft continues to absorb radiation, encounter dust, and consume power. Another proposal uses the destination star's own light as a braking mechanism. A laser sail that was pushed to interstellar speeds by lasers at Earth could, in theory, reflect light from the target star as it approaches, using photon pressure to decelerate. But the light pressure from a star is enormously weaker than the focus beam of a 100 gigawatt laser array. Deceleration using starlight would take years, possibly decades, and would only work for spacecraft with extremely low mass and extremely large sails. Precisely the kind of fragile vehicles most vulnerable to dust, radiation, and system aging during the braking phase. There is no clean solution. Every proposed braking method either adds enormous mass, enormous time, or enormous fragility to the mission. The deceleration problem alone has been sufficient to kill multiple interstellar mission concepts at the design stage. And deceleration reveals something deeper about the speed paradox that connects back to the central thesis of this entire journey. Speed was supposed to defeat distance by reducing time, but the deceleration requirement adds time back in. A spacecraft that sprints at 20% of light speed for 20 years and then brakes for another 15 has not completed a 20-year mission. It has completed a 35-year mission, with the braking phase spent at low speed in the target system, fully exposed to the same duration-related hazards, radiation, power decay, system aging, that the high cruise speed was supposed to minimize. The mission did not escape time. It merely rearranged it, compressing the transit phase and expanding the arrival phase, while adding the enormous mass penalty and engineering complexity of a deceleration system on top. For crewed missions, the speed problem carries an additional biological cost. Sustained acceleration, even at modest levels, places continuous stress on the human body. 1g of acceleration, equivalent to normal Earth gravity, is comfortable and even beneficial for preventing the bone loss and muscle atrophy associated with weightlessness. But maintaining 1g of acceleration for years requires continuous fuel consumption, which feeds back into the mass problem. And acceleration significantly above 1g, the kind needed to reach high cruise speeds quickly, cause physiological stress that becomes dangerous over extended periods. Blood pools, organs shift, connective tissue strains. The human body is not built for sustained high G environments. Fighter pilots endure high G forces for seconds or minutes, not months. Some mission concepts propose constant acceleration at 1g for the first half of the journey, and constant deceleration at 1g's for the second half. This would provide artificial gravity throughout the trip and achieve remarkable speeds at the midpoint. A spacecraft accelerating at 1g continuously would reach the halfway point to Alpha Centauri in approximately 1 year of ship time and arrive at the destination in roughly 2 years of ship time, accounting for the relativistic effects. But the fuel requirements for sustained 1g acceleration across light years are so extreme that no known or proposed fuel source can provide them. The concept works beautifully in physics textbooks. It collapses instantly in engineering reality. Nuclear pulse propulsion, the concept behind Project Orion in the 1950s and 60s, proposed detonating nuclear bombs behind the spacecraft and riding the shockwaves. It remains, even now, one of the most physically plausible methods for achieving a significant fraction of light speed. The specific impulse of nuclear detonations is orders of magnitude higher than chemical rockets. The concept was studied seriously, and small-scale tests were conducted. But the engineering challenges are immense. The pusher plate that absorbs the force of each detonation must withstand repeated nuclear explosions at close range. The shock absorber system must convert violent, repeated impulses into smooth acceleration. And the total number of bombs required for an interstellar mission, including deceleration, runs into the hundreds of thousands. Fusion propulsion, using the same process that powers stars, offers theoretical exhaust velocities high enough for interstellar missions. But controlled fusion, despite decades of research and billions of dollars in investment, has never been achieved on Earth in a sustained, net energy positive form, let alone in a compact, lightweight system suitable for a spacecraft. The engineering gap between the largest fusion experiments on Earth and a functioning interstellar fusion drive is not a step. It is a chasm measured in generations of technological development. Every propulsion concept that has been seriously studied for interstellar travel faces the same fundamental tension. The faster you go, the more energy you need. The more energy you need, the more fuel or infrastructure you must carry or build. The more mass you add, the more energy you need to move it. And at every speed, the interstellar environment imposes costs, radiation from gas, erosion from dust, thermal loading on forward surfaces that scale with velocity and cannot be avoided. There is no speed at which interstellar travel becomes easy. There is only a range of speeds at which it is theoretically survivable, and within that range, every choice involves trading one danger for another. Travel at 1% of light speed, and the environmental hazards are low, but the journey to Alpha Centauri takes over 400 years. No crew can survive that. No known power source can sustain it. No mechanical system has ever operated for a fraction of that duration. Travel at 10% of light speed, and the journey shrinks to about 43 years. Within a human lifetime, barely. but the radiation from oncoming gas becomes a serious shielding problem. The dust erosion accelerates, and deceleration at the destination requires an enormous additional propulsion effort that may double the effective mission duration. Travel at 20% of light speed, and the journey takes roughly 21 years. Faster. But the forward radiation environment becomes extreme. The dust impacts become individually destructive. The shielding mass becomes a dominant fraction of the spacecraft's total weight, and deceleration, if attempted at all, demands either a second propulsion system of equal power to the first, or a braking technology that does not yet exist. Travel at 50% of light speed, and the journey shrinks to under 9 years. Fast enough to feel almost reasonable. But the interstellar medium is now a weapon. Each hydrogen atom strikes with the energy of a high-energy accelerator particle. Each dust grain strikes with the energy of a rifle bullet. The thermal load on the forward surface requires active cooling systems that add mass and complexity. And deceleration from 50% of light speed is so energy intensive that no proposed system can accomplish it without dwarfing the mass of the spacecraft itself. This is the speed paradox. Not a puzzle with a clever solution, a genuine physical contradiction that emerges from the laws of the universe as they apply to travel between stars. Slow down and time destroys you. Speed up and the environment destroys you. The window between those two outcomes is narrow, demanding, and unforgiving. And there is one more dimension to this paradox that rarely appears in the public conversation about interstellar travel. Even if a spacecraft could accelerate to a significant fraction of the speed of light, even if it could shield against the radiation and survive the dust, even if it could decelerate and enter orbit around another star, it must navigate to get there. And navigating across interstellar distance is not the same as navigating within a solar system. Stars move. Proxima Centauri is not sitting still in space, waiting to be visited. It is orbiting the center of the galaxy at a velocity of roughly 22 kilometers per second relative to the Sun. Over the course of a multi-decade journey, the target star shifts position by a measurable amount. The spacecraft must aim not at where the star is when it launches, but at where the star will be when it arrives. This requires precise knowledge of the star's motion, precise knowledge of the spacecraft's own velocity and trajectory, and the ability to make mid-course corrections across a journey of trillions of kilometers. Within the solar system, navigation corrections are routine. Ground-based tracking stations measure the spacecraft's position using radio signals and send updated trajectory commands. The turnaround time is minutes or hours. Errors are caught and corrected quickly. Between the stars, the communication delay stretches to years. A navigation error detected by an onboard system cannot be verified by ground controllers in any useful time frame. The spacecraft must trust its own sensors, its own star trackers, its own calculations, across a journey where a pointing error of a fraction of a degree at departure translates to a miss distance of billions of kilometers at arrival. And navigation instruments degrade. Star trackers accumulate radiation damage, gyroscopes drift, accelerometers lose calibration. The same aging processes that threaten every other system on board also threaten the system responsible for knowing where the spacecraft is and where it is going. A spacecraft that left Earth pointed precisely at its target may, after decades of sensor drift and uncorrected errors, find itself aimed at empty space, arriving in a region where there is nothing to orbit, nothing to study, and no destination to justify the journey. There is a deeper dimension to the navigation problem that has no equivalent within the solar system, and it emerges from the nature of interstellar space itself. It is featureless. Within the solar system, navigation is anchored to known objects. Ground-based tracking stations measure the spacecraft's radio signal and calculate its position relative to Earth. The positions of planets, moons, and asteroids are known with extraordinary precision, and a spacecraft can use them as reference points, gravitational waymarks that confirm where it is and where it is heading. If a trajectory drifts, the drift is caught quickly because there are objects nearby whose positions are known. Between the stars, there are no such waymarks. The spacecraft crosses a void that contains no planets, no moons, no asteroids, nothing large enough or close enough to serve as a navigational reference. The stars themselves are visible, of course, and a star tracker can measure the angles between distant stars to determine the spacecraft's orientation in space. But orientation is not position. Knowing which direction you are pointing is not the same as knowing where you are. Position requires measuring how far you have traveled, and in a featureless void, that measurement depends entirely on the spacecraft's own instruments, its accelerometers, its clock, its knowledge of its own velocity. And velocity measurement across interstellar distance is unforgiving. An error of 1 meter per second in the spacecraft's measured velocity, a discrepancy so small it would be insignificant on a mission to Mars, produces a positional error that grows linearly with time. Over 1 year, that single meter per second of undetected velocity error translates to roughly 31 million meters of positional drift, over 30,000 kilometers. Over 40 years, it becomes more than 1 billion kilometers. The spacecraft does not know it has drifted because there is nothing outside the window to compare against. No nearby object to reveal the discrepancy. No ground station to measure the error from an external vantage point. The onboard instruments say the spacecraft is on course, because the onboard instruments are the source of the error. Solar system missions catch errors like this routinely because the turnaround time for ground-based tracking is minutes or hours, and the distances are short enough that small errors remain small. Interstellar missions have no such correction loop. The error accumulates in silence, compounding across trillions of kilometers of void. Undetectable until the spacecraft approaches its destination and discovers that the star it was aiming for is not where the onboard navigation predicted it would be. The speed paradox does not have a resolution within current physics or engineering. It has only trade-offs. Every interstellar mission design is an exercise in choosing which dangers to accept and which to try to mitigate, knowing that mitigation in one area often creates vulnerability in another. What this means, when the arithmetic is finished and the mission concepts are laid out side by side, is that the distance between stars does not yield to speed the way distance within a solar system does. It resists. It imposes costs at every velocity. It punishes caution and punishes ambition with equal indifference. And it forces every mission designer, whether planning for a robotic chip or a crewed vessel or a city-sized generation ship, to confront the same fundamental question. Can anything humans build at any speed survive the crossing? The answer depends on what is crossing. And the differences between what can be sent, what can be crewed, and what can be sustained across the timescales that interstellar distance demands reveal the final dimension of this problem. The one that determines whether the space between stars is a barrier that will eventually be crossed, or a test that no existing system is designed to pass. Every interstellar mission concept ever proposed falls into one of three categories: a robotic probe sent without a crew, carrying instruments and a communication system and nothing else; a crewed spacecraft, carrying human beings and everything they need to survive; or a generation ship, carrying not just a crew, but an entire self-sustaining community designed to reproduce, grow, and endure across centuries of travel. Each of these categories was invented to solve a different version of the distance problem. Each one avoids the worst vulnerability of the others, and each one, when examined honestly, encounters its own version of the same unforgiving truth. The distance between stars does not care what you send. It applies its arithmetic equally. It strips away different things from different missions, but it strips away something from all of them. Start with the robotic probe, because it is the most realistic near-term option and the one that appears, at first glance, to sidestep the worst dangers. A robotic probe does not breathe. It does not eat. It does not suffer from radiation-induced cancer or bone density loss or psychological breakdown. It does not need a social structure, a government, a medical bay, or a food supply. It can be made small, light, and radiation hardened. It can tolerate temperature extremes that would kill a human in seconds. It can operate in a vacuum without complaint. It can be accelerated at forces that would crush a human body. In every measurable way, a robotic probe is better suited to interstellar travel than a human being. But a robotic probe cannot think the way a human thinks. It cannot adapt to the unexpected. It cannot look at something it has never seen before and decide in real time what to do about it. Every response it makes must either be pre-programmed or generated by an onboard artificial intelligence system, and both of those options carry limitations that become severe across interstellar distance. Pre-programmed responses work only for anticipated situations. The designers of the probe must imagine, before launch, every scenario the probe might encounter and write instructions for each one. For a flyby of a known star system, this is challenging but feasible. For a mission that encounters something genuinely unexpected, a debris field, an electromagnetic environment that disrupts sensors, a planetary system arranged in a configuration no model predicted, the pre-programmed response set may not contain an appropriate answer. The probe does what it was told to do, even when what it was told to do is wrong, because there is no one on board to override the instructions and no way to get new ones from Earth in less than several years. Onboard artificial intelligence could, in theory, fill this gap. A sufficiently advanced system could assess novel situations, weigh options, and make decisions in real time without waiting for ground commands. But artificial intelligence systems are themselves vulnerable to the same environmental hazards that threaten every other system on the spacecraft. Radiation-induced bit flips can corrupt decision-making algorithms. Sensor degradation can feed the system false data that leads to incorrect conclusions. And the long-term reliability of software systems running continuously for decades in a high radiation environment is entirely untested. No artificial intelligence system in existence today has been validated for autonomous operation across the timescales that interstellar travel demands. The longest running software systems on Earth, banking platforms, air traffic control networks, industrial controllers, are maintained by teams of human engineers who monitor performance, patch errors, and replace failing hardware. An interstellar probe would have none of that. Its software would need to function without maintenance, without updates, and without correction for decades. Every bug it launched with would still be there when it arrived. And the probe cannot repair itself. Not in any meaningful sense. It can switch to backup systems when primary systems fail, but backup systems are finite. A probe that launches with triple redundancy on every critical system is robust for the first decade. After 2 decades, some backups have been consumed. After 3, more. By the time the probe reaches its destination, the margin between full capability and total failure may be a single remaining component in each critical chain. One more failure in any system, and the probe that crossed 4 light years of space delivers nothing. The deepest limitation of robotic probes, however, is not engineering. It is purpose. A robotic probe can collect data. It can take images. It can measure magnetic fields and atmospheric spectra and surface temperatures. What it cannot do is make the kind of integrated, intuitive, judgment-based assessments that the most important scientific discoveries have always required. The history of exploration on Earth and in space is filled with moments where a human being noticed something unexpected, asked a question no one had thought to ask, and followed a chain of reasoning that no pre-written algorithm would have pursued. A robotic probe at Proxima b could tell us the planet's surface temperature. It could measure the composition of its atmosphere. It could photograph its terrain. But it could not stand on the surface and wonder whether the strange pattern in the rock was geological or biological. It could not decide, in the moment, to abandon the planned survey and investigate a faint anomaly at the edge of its sensor range. It could not feel the weight of the discovery and understand what it meant. This is not a sentimental argument. It is a practical one. The most valuable data from an interstellar mission would be the data no one predicted. And robotic probes are, by design, optimized for collecting the data someone predicted. The unknown unknowns, the discoveries that change everything, are the domain of minds that can improvise. And those minds, if they are to be present at the destination, must survive the crossing. Which brings us to the crewed spacecraft. And the crewed spacecraft confronts a problem that no amount of engineering can fully solve. Human beings were not designed for interstellar timescales. A human body begins to deteriorate in space within weeks. In microgravity, bones lose density at a rate of roughly 1 to 2% per month. Muscles atrophy. Fluid shifts toward the head, increasing intracranial pressure and altering vision. The immune system weakens. Cardiovascular fitness declines. These effects have been documented extensively on the International Space Station, where astronauts typically spend 6 months to a year and return to Earth requiring weeks or months of rehabilitation. An interstellar journey, even a fast one, lasts decades. The minimum trip time to Alpha Centauri at 10% of light speed is over 40 years. The physiological effects of 4 decades in space, even with artificial gravity provided by spacecraft rotation, are completely unknown. No human being has ever spent more than about 14 consecutive months in space. Extrapolating from that to 40 years is not science. It is guesswork. And artificial gravity, while it addresses the most obvious microgravity effects, does not solve everything. It does not protect against radiation exposure. It does not prevent the psychological effects of confinement. It does not address the medical reality that over 40 years, every crew member will experience the full range of human health problems, infections, injuries, chronic diseases, cancers, dental emergencies, psychiatric crises, reproductive complications, and age-related decline in an environment where the nearest hospital is light years behind and getting farther away every day. The medical infrastructure required for a multi-decade crewed interstellar mission is staggering to contemplate. The crew would need surgical capability, diagnostic imaging, pharmaceutical production, or an enormous pharmaceutical stockpile, dental equipment, mental health support, and the expertise to use all of it. They would need to handle every medical scenario that might arise across 4 decades without any external consultation, without any resupply, and without any specialist who is not already on board at launch. Consider what this means in practice. A crew of 12 departs Earth on a 40-year mission to Proxima Centauri. Among them is one physician trained in surgery. 15 years into the journey, that physician develops an aggressive cancer, a statistically likely outcome given the cumulative radiation exposure. Within 2 years, the physician is incapacitated. Within 3, she is dead. The crew now has 37 years of life support monitoring, emergency medicine, and potential surgical need ahead of them, and their only trained surgeon is gone. A second crew member studied field medicine before departure, but has never performed an appendectomy, never set a compound fracture under anesthesia, never diagnosed an internal bleed using only a portable ultrasound. The gap between that crew member's training and the capability that was lost is not a gap that can be closed by reading a manual. The pharmaceutical problem is equally concrete. Modern medications have shelf lives. Most oral medications maintain full potency for 2 to 5 years under ideal storage conditions. Some degrade faster. Antibiotics, anesthetics, anti-seizure medications, cardiac drugs, each has its own degradation curve, and most of those curves were characterized for Earth-based storage, not for the radiation-saturated, temperature-variable interior of an interstellar spacecraft. A mission lasting 40 years would need either an enormous initial stockpile, with the understanding that much of it would be expired and potentially ineffective by the time it was needed, or the ability to synthesize medications on board. Pharmaceutical synthesis requires chemical precursors, laboratory equipment, sterile conditions, and expertise. Maintaining all of those across decades in a sealed vehicle without resupply adds another layer of complexity to an already overwhelming life support challenge. Psychiatric emergencies present a different kind of unsolvable problem. If a crew member experiences a psychotic episode, a severe depressive crisis, or a violent breakdown, the options on Earth include hospitalization, medication adjustment under close supervision, physical separation from potential victims, and access to trained psychiatric professionals. On an interstellar spacecraft, the crew cannot hospitalize a colleague. They cannot transfer a dangerous individual to another facility. They cannot call for a replacement. They must manage the crisis within the same sealed volume, with the same small group of people, with whatever medications remain effective, and with whatever psychiatric training someone on board happens to have. A single, severe psychiatric event could destabilize the social dynamics of the entire crew for the remainder of the mission. And across 4 decades of confinement, the probability of at least one such event is not low. It is near certain. On Earth, medical care depends on a vast support network. A surgeon operates in a hospital staffed by nurses, anesthesiologists, radiologists, pathologists, pharmacists, and maintenance technicians. Behind the hospital is a supply chain that delivers drugs, equipment, sterile materials, and replacement parts. Behind the supply chain is an industrial base that manufactures those materials. Behind the industrial base is a civilization. A crewed interstellar spacecraft would need to reproduce enough of that chain in miniature to handle any medical event that 40 years of human biology might produce. And it would need to do so within the mass and volume constraints of a vehicle that must also carry propulsion systems, power systems, navigation systems, communication systems, radiation shielding, food production, water recycling, atmosphere management, and everything else a sealed habitat requires. The psychological dimension is equally daunting. Extended isolation studies on Earth, including the Mars 500 experiment, where 6 volunteers were sealed in a simulated spacecraft for 520 days, have documented depression, sleep disruption, cognitive decline, interpersonal conflict, and motivational collapse, all within less than 2 years. An interstellar crew would face decades of confinement in a space no larger than a modest building, with the same small group of people, with no possibility of leaving, no possibility of receiving visitors, and no possibility of rescue if the social structure breaks down. Every submarine crew, every Antarctic winter rover team, every long-duration space station crew has had one psychological safety net that an interstellar crew would not. The knowledge that the isolation is temporary, that the mission will end, that home is reachable. An interstellar crew, particularly on a one-way mission, has none of that. The psychological literature is clear that open-ended confinement without a foreseeable return produces fundamentally different stress responses than time-limited isolation. It is not the same problem made longer. It is a different problem entirely. Suspended animation, the idea of placing crew members in a state of biological stasis for the duration of the transit, appears in nearly every public discussion of crewed interstellar travel as though it were a minor technical detail awaiting solution. It is not. As of 2026, no method exists for safely and reversibly suspending human biological function for extended periods. Cryopreservation, the freezing of biological tissue for later revival, works for individual cells and small tissue samples. It does not work for whole organs, let alone whole human bodies. The formation of ice crystals during freezing destroys cell membranes and tissue structures at a scale that current technology cannot prevent or repair. Research into torpor, a state of reduced metabolic activity similar to hibernation in some animal species, has shown preliminary promise for short-duration applications, days or weeks. No primate has ever been placed in sustained torpor. The metabolic suppression required, lowering core body temperature, slowing heartbeat to a fraction of its normal rate, and maintaining organ perfusion at levels just above the threshold of cell death, has been achieved in rodents for hours. Scaling that to a human body, which is orders of magnitude more massive and metabolically complex, across years rather than hours, remains beyond any demonstrated capability. Extending it to years or decades is not an incremental engineering challenge. It is a fundamental biological problem whose solution, if it exists, may be generations away. Suspended animation is not a bridge that has not been built yet. It is a bridge whose other shore has not been found, which leaves the generation ship. The concept that acknowledges, with brutal honesty, that no single human crew can survive the crossing, and proposes instead to send a self-sustaining population that lives, reproduces, and dies on board, with the expectation that the people who arrive at the destination will be the descendants, perhaps many generations removed, of the people who departed. The generation ship is the most ambitious and the most honest interstellar mission concept. It does not pretend that the journey can be shortened to a single lifetime. It does not rely on technologies that do not exist. It accepts the timescale for what it is and asks whether a human community can endure it. The answer, measured against everything known about human societies, is deeply uncertain. A generation ship is not a spacecraft with passengers. It is a sealed civilization. It must produce food indefinitely, not from stored supplies, but from onboard agriculture, aquaculture, or synthetic biology systems that cycle nutrients without loss across centuries. It must recycle water and atmosphere with near-perfect efficiency. Because every molecule of oxygen and every liter of water that is lost forever. It must maintain genetic diversity across a breeding population large enough to avoid the health consequences of inbreeding over multiple generations. Population genetics research suggests a minimum viable population for a multi-century journey of at least several hundred individuals, and some estimates place the number in the thousands. It must govern itself over centuries, without external authority, without trade partners, without the economic and political pressures that have shaped every human institution in history. The longest-lasting human institutions, certain religious orders, a handful of universities, some national governments, have endured for roughly 1,000 years at most, and every one of them operated within a larger civilization that provided context, resources, and accountability. A generation ship would have none of that. Its government would need to remain functional, legitimate, and accepted across generations of people who were born on board, who never chose the mission, who never saw Earth, and who may not share the values or priorities of the people who launched it. History offers no example of a sealed, self-governing community maintaining social cohesion across centuries without external contact. The closest analogies, isolated island populations, remote monasteries, and long-duration submarine deployments are all imperfect. None lasted for centuries. None were completely sealed. None operate without the psychological anchor of knowing that the outside world existed and could, in principle, be reached. The generation ship must also maintain its own technology, not just operate it, maintain it, repair it, replace it. The mechanical and electronic systems that keep the ship habitable, the air recyclers, the water purifiers, the power systems, the hull integrity monitors, the navigation computers must function for the entire duration of the voyage. Centuries. And they must be serviced by crew members who did not build them, who were trained by people who did not build them, who learned from people who may have been several generations removed from the original engineers. The knowledge required to maintain a starship is vast, specialized, and perishable. Skills that are not practiced are forgotten. Disciplines that are not valued by the current generation are abandoned. Technical knowledge that was critical at departure may be lost by the third or fourth generation, and the systems that depend on it will eventually fail without anyone on board who understands how to fix them. The ecological challenge alone may be disqualifying. A generation ship must function as a closed biosphere, a sealed ecosystem where every output becomes an input, and nothing is wasted. Plants convert carbon dioxide into oxygen and produce food. Human and animal waste is composted and returned to the soil. Water is purified and recycled. Atmospheric composition is maintained by the balance between photosynthesis and respiration. In theory, this is achievable. Earth itself is a closed biosphere, and it has sustained life for billions of years. In practice, the only serious attempt to build a closed biosphere on Earth failed. Biosphere 2, a 3.14-acre sealed facility in Arizona, was constructed in the late 1980s as an experiment in closed ecological systems. It contained multiple biomes: rainforest, ocean, desert, savanna, and agricultural areas, all sealed under glass with the intention of operating without material exchange with the outside world. 2 missions were attempted, the first beginning in 1991, with 8 crew members sealed inside for 2 years. The results were sobering. Oxygen levels dropped from 21% to roughly 14%, equivalent to an altitude of roughly 17,000 feet, caused by unexpected microbial activity in the soil consuming oxygen faster than plants produced it. Carbon dioxide fluctuated unpredictably. Pollinating insects died off. Certain plant species outcompeted others, destabilizing the ecosystem. Morning glory vines and cockroaches became dominant. Several food crops failed. The crew experienced persistent hunger. The group fractured into factions that stopped speaking to each other. Biosphere 2 was not in space. It was sitting on the surface of the Earth, in a temperate climate with sunlight streaming through its glass panels. It had teams of scientists monitoring it from outside. It had the option, which was eventually exercised, of pumping additional oxygen in when levels became dangerous, and it still nearly failed. The ecosystem was too complex, too sensitive to initial conditions, too dependent on balances that the designers had not fully understood. A generation ship would face every one of these problems at a scale that dwarfs Biosphere 2, and without the safety net of an outside atmosphere to tap when things go wrong. Its agricultural systems would need to produce enough calories for hundreds or thousands of people, year after year, century after century, without soil depletion, without crop disease, without pest outbreaks, and without the genetic diversity of a planet's worth of seed stock. A single blight that kills a staple crop could produce a famine with no external relief possible. A failure in the nitrogen cycle could render the soil sterile within a generation. A contamination event in the water recycling system could poison the entire water supply. And then there is the question that no engineering solution can fully address: motivation. The people who board a generation ship at departure choose the mission. They understand the purpose. They accept the sacrifice. They carry the memory of Earth, the knowledge of what was left behind and why. Their children, born on board, inherit that purpose secondhand. They hear the stories. They study the mission history. They understand intellectually why the ship exists and where it is going. But what about the 3rd generation? The 5th? The 10th? These are people born into a world they never chose, traveling toward a destination they will never reach, maintaining systems they did not build, governed by rules they did not write. Their entire existence is defined by a decision made by ancestors who are now dust. The stars outside the windows never change, the walls never expand. The destination is centuries away. For these generations, the mission is not an adventure, it is a sentence. It is a life spent maintaining a vehicle for the benefit of descendants who may or may not share their values, their priorities, or their willingness to continue. History suggests that purpose fades when it is not reinforced by direct experience. Religious orders that thrived in their founding generation often weakened by the fourth or fifth. Political movements that burned with urgency at their inception become institutions, then bureaucracies, then relics. The energy that launched the mission cannot be bottled and stored for centuries. It must be regenerated continuously by each successive generation from within a sealed environment that offers no external validation and no tangible evidence that the sacrifice is worth making. If motivation fails, if a generation decides that the mission is not their mission, that the destination is not their destination, that the systems do not need to be maintained with the rigor the founders demanded, the ship does not crash. It simply degrades. Maintenance schedules slip. Training programs thin out. Critical knowledge is lost not through catastrophe, but through indifference. And by the time the next generation realizes what was lost, the skills and systems may be unrecoverable. A generation ship does not merely need to carry a population. It needs to carry a culture, a technical education system, a medical tradition, an engineering discipline, and a shared sense of purpose, and sustain all of them across the timescales that no human culture has ever been tested against. The sealed terrarium must not only keep its plants alive, it must keep its gardeners trained, motivated, and unified for longer than any nation has ever existed. This is the final dimension of the distance between stars. It doesn't merely threaten machines. It does not merely threaten bodies. It threatens the continuity of knowledge, purpose, and social cohesion that any human mission depends on. A robotic probe can lose its instruments. A crewed spacecraft can lose its crew. A generation ship can lose its civilization. And in each case, the mechanism is the same. Time. Time applied relentlessly across a distance so vast that every system, mechanical, biological, and social, is pushed beyond its demonstrated limits. The distance between stars does not kill the way most dangers kill. It does not explode. It does not strike. It does not ambush. It simply persists. It waits while radiation accumulates in the cells of the crew and the circuits of the computers. It waits while dust slowly etches the forward surfaces of the hull. It waits while power decays and backup systems are consumed, and lubricants dry and seals crack, and instruments drift out of calibration. It waits while the crew ages, while morale fractures, while the medical supplies dwindle, while the knowledge of how to repair a critical system fades from living memory. It waits while the spacecraft, which left Earth as a mission, becomes something else. An object. A shell. A monument to ambition that was not matched by endurance. A spacecraft might physically cross the space between stars. The laws of physics do not forbid it. There is no wall at the edge of the solar system. There is no barrier that prevents an object from traveling from one star to another. Objects do it all the time. Rogue comets drift between stellar systems over billions of years. Interstellar dust grains wander the galaxy for eons. The interstellar comet that passed through our solar system recently is approximately 7 billion years old, 3 billion years older than Earth itself. Crossing the distance is not the problem. Crossing it as a functioning mission is the problem. Crossing it with instruments that still work, with a communication system that can still phone home, with a crew that is still alive, with a purpose that is still intact. That is what the distance between stars makes almost impossibly difficult. And the deepest cruelty of that distance is that it is invisible. You cannot see it. You cannot feel it. When you step outside on a clear night and look up at the stars, they appear close. They appear neighborly. Proxima Centauri, when it is visible in the southern sky, is just another faint point of light, no different from the others. Nothing about its appearance warns you that the gap between that light and this ground is a hostile duration that would slowly dismantle every machine, every body, and every institution you sent across it. The stars look like destinations. The distance between them isn't a road to those destinations. It is a filter. A test of endurance applied across every system simultaneously, with no breaks, no resupply, no rescue, and no mercy for the systems that fail first. Communication is the first to go, then rescue, then real-time support, then power margins, then redundancy, then biological health, then mechanical reliability, then navigational certainty. One by one, the supports that every human mission has ever depended on are removed, not by any hostile force, but by the simple accumulation of time in a place where nothing can be replenished and nothing can be replaced. The distance between stars is not empty in a harmless sense. It is empty in the way that an ocean is empty to a person in a lifeboat. The danger is not the water. The danger is the duration. The longer you are out there, the more things go wrong. And between the stars, the duration is measured not in days or weeks, but in decades, centuries, and millennia. We are not a species that has demonstrated the ability to build machines that last for centuries without maintenance. We are not a species that has demonstrated the ability to keep humans alive and healthy in sealed environments for decades. We are not a species that has demonstrated the ability to sustain a self-governing community in total isolation for generations. We are a species that has been building spacecraft for roughly 70 years and has never sent one farther than one light day from home. The nearest star is more than 1,500 light days away. The distance between stars is more dangerous than most people think because it does not merely separate destinations. It stretches every hazard across years, decades, centuries, or longer, until survival depends less on bravery or ingenuity than on whether any machine or human body can endure the journey without help. And no machine or human body ever built has been tested against that requirement. This is not an argument that interstellar travel is impossible. The laws of physics permit it. An object can travel from one star to another. Nothing forbids it. The question is not whether the crossing can be made, but whether anything that matters about the mission can survive the making of it. Whether instruments can still collect data when they arrive. Whether a communication system can still transmit what was found. Whether a crew, if one was sent, can still function as scientists, as engineers, as human beings when they reach the other side. The danger between stars is not hidden planets. It is not monsters. It is not sudden explosions or exotic phenomena lurking in the dark. It is the slow, systematic removal of every backup system that human missions have always relied on. Communication goes first, thinning from real-time conversation to time-delayed messages to year-long silences. Rescue goes next, becoming physically impossible once the spacecraft passes beyond any conceivable intervention range. Then, the environmental hazards begin their accumulation, radiation in the cells, erosion on the surfaces, heat leaking from systems that can no longer be replenished. Then power fades, not suddenly but steadily, following the physics of decay that no engineering can reverse. Then redundancy is consumed, backup after backup spent on the failures that decades of operation inevitably produce. Then biology, if biology is present, begins its own irreversible decline. Each of these losses is survivable in isolation. Spacecraft have operated with communication delays. Crews have worked without immediate rescue options. Machines have endured radiation and thermal stress. Power systems have been carefully managed through long missions. But between the stars, every one of these losses occurs simultaneously, across the same timeline, in the same vehicle, with no possibility of correcting any of them from the outside. The question is not whether any single system can endure. The question is whether all of them can endure at the same time, for the same duration, without any one failure cascading into the others and pulling the entire mission below the threshold of viability. That is a question no one has answered. Not because the engineering has not been attempted, but because the test has never been run. The longest continuous deep space mission in history is Voyager 1, approaching 50 years of operation, and it is operating on its last reserves, with 2 instruments functioning, no redundancy, and a ground team that must wait nearly 2 full days for every command and response cycle. Voyager 1 is humanity's best data point for long-duration spaceflight endurance, and it has crossed less than 0.1% of the distance to the nearest star. The gap between what we have demonstrated and what interstellar travel demands is not a gap that better technology will automatically close. It is a gap measured in orders of magnitude of endurance, reliability, and self-sufficiency. Closing it would require not just faster engines or better shielding, but a fundamental transformation in how long and how independently human machines and human bodies can sustain themselves. It would require machines that can repair themselves for centuries, power sources that do not decay on human timescales, biological systems that can tolerate radiation environments no human has ever inhabited, social structures that can maintain cohesion and purpose across generations of total isolation. Each of these is an unsolved problem. Together, they define the true scale of the challenge that the distance between stars imposes. The stars are visible tonight. They will be visible tomorrow night. They look close enough to reach. They are not. The distance between them is where missions stop being journeys and become survival experiments. And so far, no one has designed an experiment that the distance cannot outlast.